Okay, good morning, SUPA class. Today we are starting Unit 3, and this is the beginning of Chapter 7. Right, so we're going to deal with the periodic table. A lot of this is review. There is some new stuff in here, so let's go ahead and get started. So let's start with you do have to know a little bit about the development of the table. So the first 9 elements were discovered thousands of years ago. So these were mostly solids. That are found in elemental form. And these are ones that are some of our least active. So let's see, we found iron, and there was copper, and silver, and gold, and carbon, and sulfur, and lead, and mercury, tin. Right, so we found these a long time ago. So these are the first ones that we really identified. So the rest of the elements are gases, or found mostly in compounds. So they were not identified until much later. So we didn't have, for a long time, we didn't have the equipment that we really needed to identify what a gas was, or how it worked, or what it was made of. And we had all these compounds, and we didn't understand that there was multiple things making up that compound. So eventually, during the 1800s, we developed chemical equipment and because of this, a large number of elements were identified. So there was a huge uptick in the identification of elements in the 1800s. Well, we had people trying to categorize these elements, and there were two main people that actually developed the periodic table. So both Dmitri Mendeleev and Lothar Meyer, M-E-Y-E-R, organized the periodic table by atomic weight and similar characteristics. So if we look at the periodic table, and this is today's periodic table, right, it actually follows a lot what these two did. So he grouped them by similar chemical characteristics. So we put all these group 1s together because they reacted in a similar way, and these group 2s did the same thing. So he put them in order by characteristics, but then they both put them in order by weight. And it works most of the time. So hydrogen is 1, 4, 7, 9, 11, 12, 14. So it works most of the time, but there are a few issues. Okay, there are a few issues. So here's one of them. 122, 128, 127. All right, so it doesn't always work. There are definitely some issues with weight. In 1869, Mendeleev was given credit for creating the periodic table. Why was he given credit over Lothar? Well, Mendeleev really took it a step further. Right? He used his periodic table to predict unknown elements and their properties. Okay, so Lothar kind of organized them, but he kind of just stopped there. Okay, Mendeleev went further in his writings and said, look okay, this is incomplete. There are holes in our periodic table, and he was able to predict different elements and their properties, and then they went back and they started looking for those elements, and they found them in a lot of cases. Right? So Mendeleev was actually given credit. Now today, our periodic table is based, this one's dying, on atomic number and grouped by similar chemical characteristics mostly due to the same number of valence electrons. So the reason they have similar chemical characteristics is because they have the same number of valence electrons. Now, we really need, there's a whole bunch of stuff in here, and you talked about this in your regular chem class, so there's lots of trends and lots of things that are going on in here. And we're going to go through those again. There's a couple more that we have to go in depth with, right? So we're going to add some things, but a lot of this is going to be review today. So let's entitle this Trends of the Periodic Table. So most of the trends on the periodic table are due to the attraction of outer electrons and the nucleus of the atom. All right, so our outer electrons have that negative charge, our nucleus has that positive charge. So this force of attraction between the nucleus and these outer electrons really are what gives us most of the trends on the periodic table. Which brings us to Coulomb's law. And Coulomb's law says this: the attraction between two electrical charges depends on the magnitude of the charged particles and the distance between them. And he came up with this. E equals 2.31 times 10 to the negative 19th joules per times Q1 Q2 over R squared. Right, so here's Coulomb's law. Now what is this really telling me? Well, this is E's energy, and it's usually in joules. Here's a constant. Q1 and Q2, these are our charged ions, or electrons, whatever charged particle we have. Alright, and then this is the distance. So when we're talking about Coulomb's law, what we're really talking about is this relationship here. Alright, so the Q's are magnitude. Alright, so in an atom, we're talking about the charge of the protons, the charge of the electrons, and then the distance between them. Alright, so there are two things that are going on. Alright, now, if we keep the distance the same and we increase the number of protons and electrons, so let's say we go 1 proton, 1 electron, 1 times 1 is 1, divided by whatever, okay, and then compare it to, I don't know, a nuclear charge of 10, and a number of electrons is 10, so this number keeps getting bigger. If this number stays the same, okay, it's going to change our energy. Alright, so the biggest thing, or the biggest difference when we're talking about attraction between the nucleus and the electrons is this distance, okay, because it's squared. Alright, so you may change only a little bit in distance, but in reality the attraction is going to decrease by a whole lot, right, because of that distance change. Right, so if I have two magnets that are close together, all right, you can feel that attractive force. If I just go out a little bit, those magnets, you can't feel that attraction anymore. All right, and that's got to do with this inverse square. Right, so let's write a couple things. So the attractive force between electrons and the nucleus is dependent on the nuclear charge and distance the electrons are from the nucleus. So greater the nuclear charge, stronger the attraction. But as distance increases, our attraction decreases. So we have to talk about this nuclear charge, and we have to talk about distance and how this relates into our different trends. And to talk about nuclear charge, we're going to actually talk about what's something called the effective nuclear charge. And that's labeled Z. So the effective nuclear charge is the actual charge outer electrons get from the nucleus. Alright, so let's see if I can define this for you. First of all, as we increase atomic number, the nuclear charge increases. Remember, nuclear charge is really just the number of protons in the nucleus. Okay, so our nuclear charge is really just the number of protons in the nucleus. Right, so let's say we have lithium. Right, lithium's nuclear charge is +3. Okay, why? It has 3 protons in the nucleus. Right, if we look at fluorine, its nuclear charge is +9. Because it has 9 protons in the nucleus. Okay, so there's our nuclear charge. Now, I want to flip over. Once there are inner or core electrons, the outer electrons are shielded from the nuclear charge. And the attractive force is less. This is where we get effective nuclear charge. Okay, so our effective nuclear charge is always less than the actual nuclear charge. So let's look at magnesium. Okay, so the magnesium has 12 protons, 12 neutrons. Okay, so it's got a +12 actual nuclear charge. All right, so if we draw the dot diagram, or the Bohr model, okay, we got 2 electrons in the first. We got 8 in the second. And then finally we have 2 out here in the third. So in this we have a plus 12 nuclear charge. Okay, if we're talking about these electrons right here, okay, if we're talking about these electrons right here, they actually don't feel this plus 12 nuclear charge because we have all these electrons between them and the nucleus. All right, so these do not feel a plus 12 charge. Okay, there isn't that attractive force. Now, why is that? Well, remember, so these are all electrons. Electrons all have a negative charge. So there's a repelling force between these electrons and the inner electrons. These are actually pushing these away. Okay, so these inner electrons are also interacting with these outer electrons, which is counteracting this plus 12 charge, because it's pushing them further and further and further and further and further away. So the outer electrons are repelled by the inner electrons. And we get this equation. Z effective, we just do EFF, equals the nuclear charge Z minus S. And this is called the screening constant. Now, for our purposes, and this screening constant we have to be able to figure out, but for our purposes we're going to make it simple, right? For our purposes, and it's close enough. Okay. For us, we will use the number of core electrons. Okay. So let's go ahead and look at this a couple times. So let's say that we're going left to right across the periodic table. Or across the period. And we're going to go across 3. So we're going to start with Na. And I want to actually calculate, okay, so this has 1 valence electron. I want to actually calculate what the effective nuclear charge that outer electron is feeling. All right, so if we do Z effective equals the nuclear charge minus that screening constant. Okay. So for sodium, it's got a plus 12. We count the inner electrons. So sodium has 10 inner electrons or core electrons. So the effective nuclear charge that valence electron is feeling is a plus 1. Okay, that's the charge that it's feeling from the nucleus because of all these electrons. What if we go next door to magnesium? Well, our Z effective is equal to plus 12, so that's our nuclear charge, minus 10. All right, now why is it 10? Well, if we look up here, here it is. Okay, there are still only 10 core electrons. There are 2 valence electrons now, but our Z effective is now plus 2. Okay, let's go over to phosphorus. Our Z effective is equal to plus 15. We're still only subtracting 10 because there's 10 core electrons, right? So it's a plus 5. Okay. So as we're going across the chart, okay, the effective nuclear charge is increasing. Okay, so what's happening is the number of protons is increasing, all right, but the number of core electrons stays the same. So that attractive force gets stronger and stronger and stronger. Okay, this is the basis of really a lot of our trends. So what if we're going top to bottom? So this is left to right. So this is if we're going across the periodic table. What happens to our effective nuclear charge as we go top to bottom? So if we're going top to bottom, down a group, okay, it's a whole different trend. All right, so let's say we start with Na. We just did that one. Our Z effective was equal to plus 11 minus 10, and we got plus 1. Well, what is K going to feel? Well, what are we adding? When we do this, we add a principal energy level each time. So if we go down to K, our Z effective, okay, our nuclear charge is plus 19. Our core is 18. So it still feels a plus 1. Now, does that make sense? Well, these are chemically similar, so those outer electrons are going to feel that basic same nuclear charge. Now, it's feeling the same nuclear charge. Oops. Okay. It's feeling a plus 1 from the nucleus for both of these. All right, but there's a huge difference. All right, these valence electrons are much further away because of the added PEL than this one. All right, so in potassium, the valence electrons are much further away . So the attractive force is much less. So remember, there are 2 things that we're dealing with when we're talking about the attractive force between the nucleus and the outer electrons. Okay, we're talking about the nuclear charge. That's one thing we're talking about. All right, but you're also talking about distance from the nucleus. As we get those electrons further away, the attractive force becomes less. So you have 2 things that you have to look at when we're dealing with these trends. Okay. All right. All right, so let's talk about some of these trends. How about we talk about size of atoms or ions? So when we're talking about the size of atoms or ions, we're talking about atomic radius. Drinking my coffee this morning. And our atomic radius is half the distance between bonded nuclei. All right, so if I have two atoms that are bonded together, all right, so we have this orbital overlap. Right? This distance between the two nuclei, okay, so this is d. Okay, so our atomic radius is equal to 1/2 the distance between those bonded nuclei. So we're talking about size of it. This is how it's measured. Sorry. So it's how we measure this. Now, what happens to the size of atoms or ions as we go down a group? In a group, the atomic radius increases. So as we go down the group, why is the radius getting bigger and bigger and bigger and bigger? What's the main reason? Well, the biggest thing that we're doing as we go top to bottom is we add a principal energy level. Okay? We're adding layers. So our valence electrons are probably, remember it's all probability, found further from the nucleus. So top to bottom, our atoms or ion size gets bigger because we're adding those principal energy levels. In a period going left to right, the atomic radius tends to decrease. It's not perfect.